when the scientists announced that the James Webb Space Telescope may have found a planet with a 99.7% chance of life. Reactions split almost instantly. Some people rolled their eyes, assuming it was another case of exaggerated space news. Others jumped straight to visions of alien oceans and distant civilizations. Scientists, meanwhile, did what they usually do in moments like this. They slowed down, checked the numbers, and asked very careful questions. Hi there, and welcome to Sleepy Space Traveler. I'm really glad you're here, and I hope this moment can become a pause in your day. This channel was created as a quiet space for anyone who enjoys falling asleep, to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. Here, we slow everything down. We take big ideas about space, time, reality, and existence, and turn them into simple, soothing stories you can drift off to. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space, and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from, and what time it is for you right now. And wherever you are, maybe lying in bed, settling into the night, or just looking for a moment of calm, I hope this time feels peaceful. Thank you for being here. Now, let's begin. The phrase 99.7% chance of life sounds dramatic because it is. In scientific language, especially in astronomy, probabilities that high are rarely used casually. Researchers are trained to be conservative, sometimes painfully so. Claims are hedged with caveats, uncertainties, and error bars. So when a number like 99.7% appears, it demands attention. Not because it proves anything outright, but because it signals something statistically unusual is happening. However, the first thing to understand is that this claim does not mean scientists have confirmed alien organisms. No one has observed life directly. No probe has landed. No microscope has examined alien cells. What the claim refers to is the statistical confidence that certain atmospheric signals are real and not the result of random noise or measurement error. That distinction matters. Imagine you're listening to a faint sound through a wall. You can't see what's happening, but you hear footsteps, voices, and the clinking of dishes. You might conclude with high confidence that people are in the next room. You haven't seen them, but the evidence strongly points in that direction. That's roughly where we are with this planet. The James Webb Space Telescope is not detecting life itself. It is detecting conditions and chemical patterns that, based on everything we know so far, are most easily explained by biological activity. The planet at the center of this discussion is called K2-18b. It was known to astronomers long before Webb launched. What changed is not the planet's existence, but our ability to analyze its atmosphere in detail. Webb was built specifically to answer questions like this, questions that previous telescopes could only hint at. To understand why this moment is different from past, maybe life announcements, we need to step back and look at how scientists search for life beyond Earth in the first place. For decades, the search focused almost entirely on planets that looked like Earth. Rocky, roughly the same size. Orbiting at just the right distance from a star similar to our Sun. This made intuitive sense. After all, Earth is the only example of a living planet we know. But relying too heavily on Earth as a template is a bit like assuming all houses in the universe must look like your own. It ignores the possibility that life might thrive in environments that are unfamiliar, but still chemically and physically stable. As astronomers studied more exoplanets, planets orbiting other stars, it became clear that the universe builds planets in far more varieties than our solar system alone suggests. Worlds larger than Earth but smaller than Neptune turned out to be especially common. These in-between planets don't exist here at all, yet they may be among the most widespread types of planets in the galaxy. K2-18b belongs to this category. It is about 8.6 times as massive as Earth and roughly 2.6 times larger in radius. That alone tells us it is not a rocky Earth twin. If you tried to stand on its surface, assuming it even has one, you would experience gravity noticeably stronger than Earth's. But size isn't the most important factor here. Composition is. Observations suggest that K2-18b has a thick, hydrogen-rich atmosphere. For a long time, planets like this were written off as sterile. Hydrogen atmospheres were thought to be too hostile for life as we know it. But recent models have challenged that assumption. In fact, a hydrogen-rich atmosphere can act like a very efficient blanket. It traps heat, spreads it evenly around the planet, and allows liquid water to exist over a wider range of distances from the star. Think of it like a high-quality thermal jacket. It doesn't matter as much if the sun is slightly stronger or weaker. The inside stays comfortable. This idea led to the proposal of Hycean worlds, a term combining hydrogen and ocean. These planets would have vast global oceans beneath thick hydrogen atmospheres. No continents, no dry land, just water, chemistry, and energy. At first glance, that sounds exotic, but from a chemical perspective, it's not unreasonable. On Earth, life began in water. Many of the most robust ecosystems today exist far from sunlight, powered instead by chemical energy. Deep-sea hydrothermal vents host thriving communities that would seem impossible if we didn't know they existed. K2-18b orbits a red dwarf star, which adds another layer of complexity. Red dwarfs are smaller and cooler than the Sun. They make up about 70% of the stars in our galaxy. For a long time, they were considered poor candidates for life-hosting planets because of their violent early behavior. Young red dwarfs often produce intense stellar flares that can strip atmospheres from nearby planets. But stars, like people, tend to calm down with age. After their turbulent youth, red dwarfs settle into extraordinarily stable adulthood. They burn fuel slowly and steadily, lasting for trillions of years, far longer than the current age of the universe. That stability matters. A planet orbiting a red dwarf might have an extremely long window of time for life to emerge and evolve. Even if early conditions were harsh, a thick atmosphere could survive and eventually settle into a stable state. Over billions of years, chemistry has plenty of opportunities to get creative. K2-18b sits in the habitable zone of its star, meaning temperatures could allow liquid water to exist, not on the surface necessarily, but somewhere within its atmospheric or oceanic layers. Again, habitable does not mean inhabited. It means possible. What pushed this planet into the spotlight was Webb's detection of specific molecules in its atmosphere. Webb uses a technique called transit spectroscopy, which sounds complex but is conceptually simple. when the planet passes in front of its star. A small fraction of the starlight filters through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths of light. By measuring which wavelengths are missing, scientists can identify which gases are present. It's similar to shining a flashlight through colored glass and analyzing which colors come out the other side. You never touch the glass, but you can still infer its composition. Using this method, Webb detected water vapor, carbon dioxide, methane, and most intriguingly, dimethyl sulfide, or DMS. On Earth, dimethyl sulfide is produced almost exclusively by living organisms, particularly marine life like phytoplankton. It plays a role in cloud formation and even climate regulation. Importantly, there are no known non-biological processes that produce DMS in large quantities under Earth-like conditions. That doesn't automatically mean life is responsible on K2-18b. But it does mean the simplest explanation we know involves biology. This is where the 99.7% figure comes in. It refers to the statistical confidence that the DMS signal is real, not a fluke of the data. In physics, this corresponds roughly to a 3 sigma detection. It's strong evidence, but not definitive. Science reserves its highest confidence, 5 sigma, for claims that are extremely unlikely to be false. Particle physics discoveries like the Higgs boson required that level of certainty. Astronomy, especially remote sensing, often operates under slightly different standards, but caution still applies. So, why are scientists excited but careful? Because this is the first time we've detected a combination of molecules that, together, point strongly toward biological processes on a planet that plausibly supports liquid water. Previous claims focused on single molecules or planets with less favorable conditions. This is not a smoking gun. It's more like finding smoke, heat, and the smell of cooking all at once. Here, we'll take a deeper look at K2-18b itself, its structure, environment, and why being not Earth-like may actually improve its chances of hosting life. K2-18b becomes more interesting the longer you resist the urge to compare it to Earth. In fact, one of the biggest obstacles to understanding planets like this is our tendency to treat Earth as the default blueprint for life. It's natural to do so, but it can quietly limit our imagination. To understand why K2-18b is a serious candidate for habitability, we need to unpack what kind of world it actually is, starting with what it is not. It is not a rocky planet with continents, oceans, and an atmosphere like ours. It is not a place where trees sway or mountains rise from dry land. If you could somehow visit it, the experience would feel utterly alien. Yet alien does not mean lifeless. K2-18b belongs to a class of planets that astronomers didn't even know existed until a few decades ago. These are planets larger than Earth but smaller than Neptune, often called sub-Neptunes. Our solar system has none of them, which already tells us something important. Our local experience is incomplete. Think of planet types like vehicle types. If you only studied bicycles and semi-trucks, you might conclude that vehicles come in only 2 extremes, small and slow, or massive and industrial. Then someone introduces you to cars, buses, and trains. Suddenly, the space in between becomes the most crowded and interesting part. That's what happened with exoplanets. When astronomers started discovering planets around other stars, they expected to find mostly familiar categories. Instead, they found that the most common planets in the galaxy are ones we don't have at home. Sub-Neptunes dominate the census. K2-18b sits right in that sweet spot. Its mass suggests that gravity on this planet is stronger than Earth's, but not crushing. Its radius implies that it cannot be purely rocky. The best models indicate a layered structure, a dense core, possibly rocky or icy, surrounded by deep layers of water and capped by a thick, hydrogen-rich atmosphere. This atmospheric composition is crucial. Hydrogen is the lightest element, but when present in large quantities, it creates pressure. That pressure increases the boiling point of water, allowing liquid water to exist under conditions that would otherwise turn it into vapor. In everyday terms, this is like a pressure cooker. Water boils at higher temperatures inside one, even though the heat source hasn't changed. On K2-18b, pressure does the same job. Even if surface conditions are extreme, somewhere below the atmosphere there may be layers where liquid water is stable. This is where the idea of a global ocean comes in. Instead of continents and shallow seas, K2-18b may have a continuous ocean wrapping the entire planet. No shorelines, no dry land. Just water extending downward for tens or even hundreds of kilometers, transitioning into high-pressure ice or supercritical fluids deeper below. At first, this sounds like science fiction, but we already have partial analogs right here on Earth. Europa, a moon of Jupiter, is believed to harbor a global ocean beneath an icy shell. Enceladus, a moon of Saturn, sprays water vapor and organic compounds into space from subsurface oceans. Neither looks remotely like Earth's surface, yet both are considered promising targets in the search for life. The key lesson is that life does not require beaches. Life requires three things: a solvent, usually water, a source of energy and chemistry that allows complexity to build. K2-18b plausibly checks all three boxes. The energy source does not have to be sunlight. On Earth, entire ecosystems exist in total darkness, powered by chemical gradients. Bacteria thrive by feeding on sulfur compounds, methane, and hydrogen. These same chemicals appear to be present on K2-18b. The presence of methane and carbon dioxide together is particularly interesting. In isolation, each can exist without life. Together, they suggest a dynamic atmosphere where chemical reactions are constantly being driven away from equilibrium. In simple terms, the atmosphere looks chemically busy. This is important because lifeless planets tend to drift toward chemical calm. Over time, reactions settle. Reactive gases disappear unless something keeps replenishing them. On Earth, that something is life. You can think of it like a bathtub. If the faucet is off, water levels eventually stabilize. If the tub is constantly overflowing, something must be adding water. On K2-18b, certain gases appear to be continuously replenished. Now, let's talk about the star. K2-18b orbits a red dwarf star called K2-18. Red dwarfs are smaller, cooler, and dimmer than the Sun. From far away, they look unimpressive. But they are the most common stars in the universe. For a long time, red dwarfs were considered poor hosts for life because planets need to orbit very close to them to receive enough warmth. That closeness exposes planets to stellar flares and radiation, especially early in the star's life. However, this picture has changed. Red dwarfs are like unpredictable teenagers who eventually become calm, reliable adults. Their early years are chaotic, but after a few 100 million years, they settle down and remain stable for trillions of years. That gives planets enormous amounts of time to recover, evolve, and stabilize. A thick atmosphere helps enormously here. Hydrogen-rich atmospheres are resilient. They absorb radiation, redistribute heat, and protect underlying layers. Even if early flares stripped away some material, enough could remain to support long-term stability. K2 18b appears to orbit within the star's habitable zone. But it's important to clarify what that means. The habitable zone is often described as the Goldilocks zone, not too hot and not too cold. That's a simplification. In reality, the habitable zone is a range of distances where liquid water could exist somewhere on or within a planet, given reasonable atmospheric conditions. For K2 18b, those conditions are not surface level. They are atmospheric and subsurface, but that still counts. This reframes habitability entirely. Instead of asking, could humans live there? Scientists ask, could chemistry organize itself there in a stable way for long periods? Those are very different questions. And that brings us back to why this planet matters. K2 18b forces us to loosen Earth-centric thinking. It suggests that life-friendly environments may be far more common than previously thought, because they do not require Earth's exact recipe. You don't need continents, you don't need oxygen, you don't even need sunlight at the surface. You need stability, energy, and time. K2 18b has likely had billions of years to evolve chemically. Its star is old. Its orbit is stable. Its atmosphere appears thick and persistent. These are not the conditions of a fragile world. Of course, there are still open questions. At extreme pressures, water behaves differently. Chemistry changes. Biological processes we know may not function the same way. But life is not obligated to resemble Earth life. That idea makes some people uncomfortable. It feels safer to imagine alien life as green versions of ourselves. But biology is opportunistic. It exploits whatever conditions exist. On Earth, life thrives in boiling acid, frozen ice, and crushing depths. That diversity should caution us against assuming narrow limits elsewhere. K2 18b may host life that would be unrecognizable to us. It may host no life at all. But it occupies a category that makes life plausible in a serious, testable way. And that is the key difference between this discovery and previous ones. We are no longer speculating blindly. We are analyzing data, testing models, and identifying specific chemical signatures that narrow the possibilities. In the next part, we'll dive deeper into how the James Webb Space Telescope actually made these measurements, why its instruments are uniquely suited to this task, and how scientists separate genuine signals from noise. This is where physics, engineering, and statistics come together. To understand why the observations of K2 18b carry so much weight, we need to look closely at how the James Webb Space Telescope actually gathers its data. This is where the story shifts from planetary speculation to the practical mechanics of measurement, because extraordinary claims only matter if the instruments behind them are trustworthy. James Webb was not designed to take pretty pictures of distant planets. Its real strength lies in something far more subtle, its ability to analyze light with extreme precision. Webb is, at its core, a giant infrared spectrometer. It doesn't just see objects, it dissects the light they emit or reflect and breaks it into its component wavelengths. Every atom and molecule interacts with light in a unique way. When light passes through a gas, certain wavelengths are absorbed, depending on the chemical bonds present. This creates a pattern of dark lines in the spectrum, known as absorption lines. You can think of these patterns as molecular fingerprints. The principle is simple, even if the execution is not. Imagine sunlight passing through stained glass. The colors that come out depend entirely on what the glass is made of. Webb does something similar, except the glass is the atmosphere of a planet hundreds of trillions of kilometers away. The key technique used here is called transit spectroscopy. When a planet passes in front of its star from our point of view, a tiny fraction of the starlight filters through the planet's atmosphere before reaching the telescope. That filtered light carries information about the gases it encountered along the way. This is an incredibly delicate measurement. We are talking about detecting changes in brightness on the order of a few parts per million. It's like trying to determine the ingredients of a soup by analyzing the steam rising from it across an entire city. Previous telescopes could attempt this, but they were limited in sensitivity, wavelength coverage, and stability. James Webb was built to overcome those limitations. Webb operates primarily in the infrared. This matters because many biologically relevant molecules absorb light most strongly at infrared wavelengths. Water vapor, methane, carbon dioxide, and dimethyl sulfide all leave clearer fingerprints in this range. It's similar to how some objects are invisible under normal light but glow brightly under infrared cameras. Webb is essentially looking at the universe through thermal and chemical contrast rather than visual appearance. Another advantage is Webb's location. Orbiting far from Earth, it avoids atmospheric interference. Earth's atmosphere absorbs and emits infrared light, which makes precise measurements from the ground extremely difficult. Webb sidesteps this problem entirely. Now, detecting a molecule once is not enough. Spectroscopy involves averaging many transits over time. Each time K2-18b passes in front of its star, Webb collects data. Those datasets are combined, cleaned, and statistically analyzed to reduce noise. Noise is the enemy here. Noise can come from instrumental drift, stellar activity, cosmic rays, and countless other sources. The challenge is distinguishing a real signal from random fluctuations. This is where statistical confidence enters the discussion. When scientists say a signal is detected at 99.7% confidence, they mean that the probability of the signal arising from random noise is only 0.3%. In statistical terms, this corresponds to a 3 sigma detection. To make that intuitive, imagine flipping a fair coin. Getting heads once tells you nothing. Getting heads 10 times in a row starts to feel suspicious. At some point, you begin to question whether the coin is fair. Statistics helps define where that point lies. In astrophysics, 3 sigma detections are taken seriously, but not declared final. 5 sigma is the gold standard for discovery. However, 3 sigma is often enough to justify excitement, follow-up observations, and further investment. For K2-18b, the detection of water vapor and carbon-bearing molecules had already reached strong confidence levels in earlier studies. What changed with Webb was the detection of dimethyl sulfide. DMS is not just another molecule on the list. Its importance comes from its role in Earth's biosphere. On Earth, DMS is produced primarily by marine microorganisms. It enters the atmosphere, affects cloud formation, and plays a role in climate regulation. Crucially, there are no well-established non-biological processes that generate large quantities of DMS under Earth-like conditions. That does not mean non-biological pathways are impossible elsewhere, but it does mean biology is the simplest known explanation. In science, the simplest explanation consistent with the data is often preferred, but only cautiously. This is known as Occam's razor. It's not a rule, but a guideline. Imagine walking into a kitchen and finding dirty dishes, a warm stove, and the smell of food. One explanation is that someone has been cooking. Another is that a complex chain of non-human events produced the same outcome. Both are logically possible, but one is far more reasonable. That's where K2-18b currently stands. The atmospheric chemistry appears out of equilibrium. Methane and carbon dioxide coexist in ratios that suggest constant replenishment. Water vapor is present, and DMS appears alongside them. None of these alone proves life. Together, they form a pattern that is difficult to explain through purely geological or photochemical processes. However, scientists are careful to emphasize what is still unknown. We do not know the planet's exact temperature profile. We do not know the depth or composition of its ocean. We do not know how chemistry behaves under its specific pressures and radiation environment. And we do not yet have laboratory experiments that fully replicate these conditions. This uncertainty is not a weakness. It is an honest boundary. Astronomy often works this way. We build models based on known physics and chemistry, compare them to observations, and adjust when mismatches appear. Over time, the models improve. In this case, multiple independent teams analyzed Webb's data using different assumptions and methods. The results were broadly consistent. That consistency matters more than any single analysis. Another point worth clarifying is the role of the host star. Red dwarf stars can be active. Stellar flares could, in theory, influence atmospheric chemistry and mimic biological signatures. Researchers accounted for this by modeling the star's activity and comparing it with the observed molecular patterns. The signals detected do not correlate strongly with flare events, which strengthens the case that they originate in the planet's atmosphere. Still, this is not the final word. Science progresses by replication. Future Webb observations will target K2-18b again, refining measurements and testing alternative explanations. Other telescopes, current and future, may provide complementary data. If the DMS signal persists across multiple observations and instruments, confidence will increase. If it disappears, the hypothesis will be revised or abandoned. This is how science protects itself from wishful thinking. What makes this moment different from past maybe-life claims is not enthusiasm, but maturity. The field of exoplanet science has grown up. Researchers understand the pitfalls. They have been burned before by premature conclusions. As a result, the tone surrounding K2-18b is cautious but serious. No one is declaring victory. No one is dismissing the possibility either. Instead, the community is treating this as what it is: the strongest atmospheric evidence so far for a potentially living world beyond our solar system. In the next part, we'll examine dimethyl sulfide in detail: what it is, why it matters chemically, and why its detection is both exciting and problematic at the same time. This is where biology, chemistry, and planetary science intersect most sharply. Dimethyl sulfide, often shortened to DMS, is the molecule that turned a careful scientific discussion into a global headline. Not because it guarantees life, but because it sits at a rare intersection between chemistry and biology that scientists pay very close attention to. To understand why DMS matters, it helps to start with a simple question. How do scientists decide whether a molecule might indicate life? In astrobiology, the focus is not on finding molecules that can be produced by life. Almost everything can be. The focus is on molecules that are difficult to maintain without life. Life has a habit of pushing chemical systems out of balance. It takes simple ingredients and rearranges them into states that would normally collapse back into equilibrium. Earth's atmosphere is a perfect example. Oxygen should not exist in large quantities for long. It reacts with almost everything. Without constant replenishment by photosynthesis, oxygen would disappear on geological timescales. The fact that it doesn't is a sign that something is continuously producing it. DMS plays a similar role, but in a more specific way. On Earth, dimethyl sulfide is produced almost entirely by living organisms, especially microscopic marine life such as phytoplankton. These organisms create sulfur-containing compounds as part of their metabolism. When those compounds break down, DMS is released into the atmosphere. What makes DMS special is not just that it is biological, but that it is fragile. It does not persist easily. Sunlight breaks it apart. Chemical reactions remove it. Without a steady source, it disappears quickly. That means that if you detect DMS in an atmosphere, something must be actively producing it. This is why the detection of DMS on K2-18b caused such interest. It suggests ongoing chemistry, not a fossil trace from the distant past. However, caution is necessary. Biology is not the only imaginable source of DMS. It is simply the only known dominant source on Earth. Other planets may host unfamiliar chemistry. So, scientists asked a critical question. Could DMS be produced abiotically without life under the conditions expected on K2-18b? Researchers explored several possibilities. One idea involved photochemistry, where ultraviolet radiation drives complex reactions in the atmosphere. Another involved volcanic activity, where sulfur compounds might be released from a planet's interior. A third considered interactions between hydrogen-rich atmospheres and surface chemistry. So far, none of these mechanisms have convincingly reproduced the observed DMS levels in realistic models. Some can produce trace amounts, but not at the scale suggested by the data. To use an analogy, it's like finding smoke that looks and smells like it's coming from a kitchen. You can imagine scenarios where smoke appears without cooking, but recreating all the details at once becomes increasingly unlikely. Another reason DMS matters is how it fits into the broader chemical picture of K2-18b's atmosphere. The planet's atmosphere does not appear chemically settled. Methane and carbon dioxide coexist in proportions that are difficult to maintain without continuous input. Water vapor is present. Hydrogen dominates the background. This is a chemically active environment. If DMS were detected in isolation, it would be intriguing but not compelling. Combined with other gases that suggest dynamic processes, it becomes more meaningful. Think of it like hearing multiple instruments playing together rather than a single note. the pattern matters more than any individual sound. Another important factor is the planet's environment. K2 18b is likely warm but not scorching. Models suggest temperatures compatible with liquid water somewhere below the atmosphere. Pressure would be high, but not necessarily prohibitive for chemistry. On Earth, life exists under conditions once thought impossible. Deep-sea organisms live under crushing pressure and near-boiling temperatures. Extremophiles thrive in acidic lakes and radioactive waste. Biology adapts. This doesn't mean life must exist on K2 18b. It means we cannot rule it out simply because conditions are unfamiliar. Now, let's address the 99.7% chance phrase more carefully. This number does not mean there is a 99.7% chance that life exists on K2 18b. That interpretation would be incorrect. What it means is that scientists are 99.7% confident that the DMS signal detected in the data is real, not a statistical artifact. In other words, the molecule appears to be present in the atmosphere with high confidence. This distinction is subtle but crucial. Statistics tell us whether a signal exists. They do not tell us what causes it. To understand this, imagine a medical test that detects a specific marker in blood. The test may be 99.7% accurate at detecting the marker. That does not mean there is a 99.7% chance the patient has a particular disease. Interpretation requires context, additional tests, and understanding alternative causes. Astronomy works the same way. The detection of DMS is robust. The interpretation of that detection is still open. This is why scientists emphasize follow-up observations. Webb can observe K2's 18b multiple times, improving signal strength and refining models. Future telescopes may detect related molecules or confirm patterns that strengthen or weaken the biological hypothesis. Another question often raised is whether contamination could explain the signal. Could DMS come from Earth, instruments, or data processing? This possibility is taken seriously. Calibration procedures are rigorous. Instrument backgrounds are carefully characterized. Independent teams analyze the same data using different methods. So far, contamination has not provided a convincing explanation. The importance of DMS also extends beyond this one planet. If confirmed, it suggests that life may commonly alter planetary atmospheres in detectable ways. It would validate decades of theoretical work predicting that biosignatures could be observed remotely. This would represent a turning point. Before Webb, discussions of life detection were largely speculative. Scientists debated which molecules might matter, how sensitive instruments would need to be, and whether detection was even feasible. Now, those debates are being tested against real data. Even if K2 18b turns out to host no life, the process itself is transformative. We are learning how to interpret complex atmospheres, how to avoid false positives, and how to refine our criteria. In science, progress often comes from investigating promising leads that ultimately fail. Each failure improves future success. But if the DMS signal holds up, and if alternative explanations continue to fall short, the implications are profound. It would suggest that life arises readily when conditions allow. That biology is not a rare accident, but a common outcome of chemistry and time. That does not mean intelligent life is common. It does not mean civilizations are everywhere. It means the universe may be biologically active in ways we are only beginning to measure. In the next part, we'll explore what this discovery implies for how scientists define habitability and how it reshapes the search for life beyond Earth. We'll also look at how Earth-centric assumptions have limited past searches, and why K2-18b forces a broader perspective. If K2-18b has taught scientists anything so far, it is that our old definition of habitable was far too narrow. For decades, the search for life beyond Earth focused on finding planets that looked as much like Earth as possible. Rocky, about the same size, orbiting a sun-like star, with temperatures that allow liquid water on the surface. This approach made sense. Earth is the only example of a living planet we know. When you only have one data point, it's natural to treat it as the template. But nature rarely respects our templates. K2-18b does not look like Earth. It is larger. It likely has no solid surface in the way we imagine continents and oceans. Its atmosphere is thick, rich in hydrogen, and more similar to Neptune's than Earth's. And yet, it may still host environments where life can exist. This realization has quietly reshaped astrobiology over the past decade. Scientists have begun moving away from the idea that life requires an Earth twin. Instead, they are exploring the idea that life requires conditions, not specific forms: liquid solvents, chemical gradients, energy sources, stability over long periods of time. Earth uses liquid water as its solvent, but water is not special because it is water. It is special because it allows chemistry to happen efficiently. If another environment provides similar chemical flexibility, life may emerge there as well. On K2-18b, models suggested that beneath the hydrogen-rich atmosphere, there could be a deep ocean. Not a shallow ocean like Earth's, but one potentially hundreds or thousands of kilometers deep. This idea leads to the concept of a Hycean world, a term introduced in recent years to describe planets with hydrogen atmospheres and global oceans. Hycean planets expand the habitable zone dramatically. Hydrogen is an excellent greenhouse gas. It can trap heat efficiently, allowing liquid water to exist farther from a star than previously thought. This means that planets orbiting dim red dwarfs, once considered marginal for life, may actually be prime candidates. But life in such an ocean would not resemble life on Earth's surface. There would be no sunlight penetrating deeply. Photosynthesis, at least as we know it, might be limited or absent. Instead, life would rely on chemical energy, much like organisms near Earth's hydrothermal vents. On our planet, entire ecosystems thrive in total darkness, powered by reactions between water and minerals. These systems do not depend on sunlight at all. They depend on chemistry. This makes the idea of life on K2-18b more plausible than it might initially sound. Another important shift involves atmospheric interpretation. For a long time, scientists assumed that biosignatures would resemble Earth's: oxygen, ozone, methane in specific ratios. But Earth's atmosphere reflects Earth's biology. Other biospheres may produce different signatures. The presence of DMS on K2-18b is exciting precisely because it was not a primary target. It emerged from a broader survey, not a narrow checklist. This suggests that life may announce itself in unexpected ways. However, this also introduces new challenges. The more flexible our definitions become, the harder it is to rule out false positives. Exotic chemistry can sometimes mimic biology. Planetary environments can surprise us, This is why the scientific response to K218b has been careful, not celebratory. Researchers are not claiming discovery. They are refining hypotheses. Follow-up observations are already planned. Webb will continue to observe K218b at different wavelengths. Scientists will look for additional sulfur compounds, for consistency across measurements, and for time variations that might indicate active processes. If DMS is truly being replenished, its concentration may fluctuate in detectable ways. There is also interest in detecting other molecules associated with biological activity, such as methyl mercaptan or dimethyl disulfide. These compounds, if found together, would strengthen the case significantly. At the same time, laboratory experiments are being conducted on Earth to test whether non-biological pathways could produce similar signals under simulated conditions. This interplay between observation and experiment is central to how science advances. Data raises questions. Experiments explore possibilities. Models are refined. What makes this moment unique is that, for the first time, the questions involve specific planets with measurable atmospheres. We are no longer asking abstract questions about life out there. We are interrogating particular worlds. This has implications beyond astrobiology. If life can exist in environments as diverse as deep hydrogen oceans, it suggests that biology may be a natural extension of planetary evolution, not a rare anomaly. Planets form. Chemistry unfolds. Under the right conditions, complexity emerges. That does not diminish Earth's uniqueness. It reframes it. Earth may not be special because it hosts life, but because it hosts a particular kind of life that led to intelligence capable of asking these questions. Another implication concerns future missions. The James Webb Space Telescope is not optimized specifically for biosignature detection. It is a general-purpose observatory, yet it has already pushed the boundaries of what is possible. Future telescopes, such as the proposed Habitable Worlds Observatory, will be designed explicitly to study Earth-like and non-Earth-like planets in detail. These missions will have greater sensitivity, broader wavelength coverage, and the ability to study smaller, cooler planets. K218b may turn out to be just the first hint in a much larger story. Even if it is ultimately explained by unknown chemistry, it will still have changed how scientists search for life. The search will become broader, more imaginative, and more cautious at the same time. There is also a cultural impact. Headlines about 97% chance of life captured public attention, but they also highlighted the gap between scientific nuance and public interpretation. Scientists have responded by emphasizing uncertainty, context, and the difference between detection and confirmation. This transparency is essential. The goal is not to declare victory, but to build understanding. Astrobiology is not about belief, it is about evidence, and evidence accumulates slowly. In many ways, K218b represents a rehearsal for a future moment when evidence becomes overwhelming, when multiple independent biosignatures align, when alternative explanations collapse under scrutiny, when a planetary atmosphere refuses to behave like any known abiotic system. That moment may come in years, or decades, or centuries, or it may never come at all. But the process of searching is already reshaping science. In the next part, we will step back and ask a broader question. What would it mean, scientifically and culturally, if life were confirmed beyond Earth? not speculation, not philosophy, but measurable consequences for physics, biology, and our understanding of the universe. If confirmed life beyond Earth were announced tomorrow, the immediate reaction would not be celebration. It would be recalibration. Science does not respond to discoveries with fireworks. It responds with questions. The confirmation of life on K218b or any other exoplanet would force scientists to re-examine assumptions that reach far beyond astrobiology. It would touch physics, chemistry, planetary science, and even the way we interpret probability itself. The first major shift would occur in biology. On Earth, life is deeply interconnected. Every organism traces its ancestry back to a common origin. All known life uses DNA or RNA, the same genetic code, and similar biochemical machinery. This shared structure has led many scientists to quietly assume that life elsewhere, if it exists, would look at least somewhat familiar. But if life emerged independently on another planet, that assumption would be tested. If the chemistry of life on K218b differs fundamentally from Earth's, different solvents, different molecular backbones, different metabolic cycles, it would mean that life is not a rare accident, but a flexible outcome of chemistry under certain conditions. Think of it like cooking. If every kitchen in the universe produced the same dish, that would suggest an extremely narrow recipe. But if kitchens across the cosmos independently invent different cuisines, all based on heat, chemistry, and available ingredients, then cooking becomes a natural consequence of kitchens existing at all. Life may be the same way. The second shift would involve planetary science. Currently, planets are classified into neat categories: rocky planets, gas giants, ice giants, super-Earths. These categories are based on mass, composition, and orbit. But life does not care about categories. It cares about environments. K218b sits awkwardly between categories. It is not a gas giant. It is not rocky. It is not Earth-like. If life exists there, it would force scientists to think less in terms of planet types and more in terms of habitable zones within planets. Habitability would become layered. Instead of asking, "Is this planet habitable?" scientists would ask, "Is there any stable region within this planet where chemistry can remain complex for long periods of time?" This is already happening in discussions about subsurface oceans on moons like Europa and Enceladus. Life may exist far from surfaces, far from sunlight, hidden beneath kilometers of ice. Exoplanets would simply extend that idea to entirely different planetary architectures. The third shift would be statistical. Right now, the Drake equation, a famous framework for estimating the number of communicating civilizations, relies on a chain of probabilities, many of which are poorly constrained. How often do habitable planets form? How often does life begin? How often does intelligence arise? If life is confirmed on a second independent world, one of those probabilities would jump dramatically. It would mean that life begins easily given the right conditions. This does not mean intelligent life is common. Microbes dominated Earth for billions of years before complex organisms appeared. Intelligence may still be rare, but it would mean that the universe is not sterile. It would be biologically active. Another consequence would involve chemistry. Many of the molecules associated with life on Earth are not unique to life. Amino acids form naturally in space. Complex organic compounds are found in interstellar clouds. What distinguishes life is not molecules, but organization. Life takes matter and arranges it into systems that persist, adapt, and replicate. If life is detected elsewhere, chemists would focus intensely on identifying the minimal conditions required for this transition from chemistry to biology. This would push laboratory research in new directions. Experiments would simulate exotic planetary conditions, high-pressure hydrogen oceans, unfamiliar temperature gradients, unusual solvent mixtures. Biochemistry would no longer be Earth-centric. It would become cosmic. There would also be implications for atmospheric science. A living planet is not in equilibrium. Life constantly pushes its environment away from chemical balance. On Earth, oxygen exists because plants continually replenish it. Without life, oxygen would quickly react away. If K2-18b shows persistent chemical disequilibrium, gases that should not coexist unless something is actively maintaining them, it would strengthen the biological interpretation. This concept, called chemical disequilibrium, is becoming a central idea in biosignature research. Instead of looking for specific molecules, scientists look for atmospheric behavior that cannot be sustained passively. It is the difference between finding a single footprint and noticing that the floor keeps being swept clean every night. One is a clue. The other implies ongoing activity. Beyond science, there would be a quieter, more subtle shift in how humans perceive themselves. Not an existential crisis, more like a perspective adjustment. For centuries, humans have oscillated between feeling central and feeling insignificant. The Copernican revolution removed Earth from the center of the universe. Modern cosmology placed us in an ordinary galaxy among hundreds of billions. Life beyond Earth would not erase humanity's importance. It would contextualize it. We would become one example among many. That realization may feel unsettling, but it can also be grounding. It reminds us that life is not a fluke to be hoarded, but a phenomenon to be understood. Importantly, confirmation of life does not mean contact. K2-18b is about 120 light-years away. Even light takes more than a century to travel between us. Communication, let alone travel, is far beyond current technology. This distance protects both sides from immediate consequences. There would be no invasion, no message, no response, just knowledge. And knowledge changes behavior slowly. Another misconception worth addressing is the idea that discovering life elsewhere diminishes the importance of Earth. In reality, it increases it. Earth would become the first known inhabited planet studied in detail from the inside. Its biosphere would become a reference point, a baseline. Protecting it would become even more important. Planetary protection policies, already in place for Mars missions, would take on new significance. Contamination concerns would expand beyond our solar system. Ethical discussions would emerge, not about aliens, but about responsibility. If life is common, does that increase our obligation to preserve environments, both here and elsewhere? If life is fragile, what does that say about our own actions? These questions are not speculative science fiction. They are extensions of real debates already happening in planetary science and environmental ethics. The discovery of possible life on K2-18b is not about answering all questions. It is about opening better ones. Science advances not by certainty, but by curiosity disciplined by evidence. At this stage, K2-18b represents a promising signal, not a conclusion. The next steps are methodical, repeated observations, independent verification, better models, more data. If future measurements reduce uncertainty and confirm biological activity. The announcement will not be dramatic. It will be careful. Scientists will say something like, "All known non-biological explanations have been ruled out within current models." That sentence will be more significant than any headline, because it will mark the moment when life stops being an Earth-only phenomenon and becomes a cosmic one. In the final 2 parts, we will zoom out even further. First, we will examine the limitations of our instruments and why claims like a 9.7% chance must always be treated carefully. Then, we will ask a final question. What does the future of life detection look like, and how close are we really to knowing whether we are alone? One of the most important lessons scientists have learned, sometimes the hard way, is that extraordinary claims demand not just strong evidence, but carefully framed evidence. This is where the famous phrase, 99.7% chance of life, becomes both powerful and dangerous at the same time. The number sounds precise. It sounds authoritative. It sounds like the kind of confidence we associate with medical diagnoses or engineering tolerances. But in astronomy, probabilities do not work quite the same way. That figure does not mean there is a 99.7% chance that aliens are swimming in hydrogen oceans on K2 and 18b. It means that, given the current models, the observed atmospheric signals are statistically unlikely to be explained by known non-biological processes. That distinction matters. Think of it like weather forecasting. If a meteorologist says there is a 99% chance of rain tomorrow, it does not mean rain is guaranteed. It means that under current atmospheric models, rain is overwhelmingly more likely than any other outcome. But those models themselves are imperfect. In exoplanet science, the uncertainty is even greater, because scientists are working with extremely limited information. All the data about K2-18b comes from tiny changes in starlight measured from 120 light-years away. We are inferring the chemistry of an alien world using shadows and spectra. It is like trying to identify a person's diet by watching their silhouette through a foggy window once every few months. This is why responsible scientists emphasize caution, even when the data looks exciting. Atmospheric models depend on assumptions about temperature, pressure, composition, cloud coverage, and internal heat. Change any of those assumptions slightly, and the interpretation can shift. Some alternative explanations for the detected molecules include unknown geochemical reactions under extreme pressure, photochemical processes not yet fully modeled, instrumental artifacts combined with statistical noise, exotic chemistry that mimics biological signatures. None of these explanations are currently favored, but science has learned not to dismiss unknown unknowns. History provides examples. In the 1970s, scientists believed methane on Mars might indicate life. Later, it turned out that geological processes could produce methane without biology. More recently, phosphine detected in Venus's atmosphere sparked excitement, only to be later re-evaluated after data processing errors and alternative explanations emerged. These episodes were not failures. They were the scientific process working as intended. Claims are made. Evidence is tested. Interpretations evolve. What makes Q18b different is not certainty, but convergence. Multiple molecules appear together. Their relative abundances match patterns that, on Earth, are associated with biological activity. The planet's environment is consistent with theoretical models of habitability. This does not prove life, but it narrows the field. The next phase of investigation will rely heavily on future observations, especially with the James Webb Space Telescope and its successors. Webb can observe the same planet multiple times across different wavelengths, looking for consistency. If the signals persist and behave as expected over time, confidence increases. Scientists will also look for context. Life does not exist in isolation. It modifies its environment in predictable ways. If one biosignature appears, others should follow. For example, on Earth, methane and oxygen coexist because life continually produces them. Without life, they would react and disappear. If K2-18b shows long-term chemical patterns that resist equilibrium, that would be harder to explain without biology. Another crucial factor is time. Geological processes tend to fluctuate. Biological systems tend to stabilize their environment over long periods. If the atmospheric composition of K2-18b remains stable across years of observation, that would strengthen the case for ongoing activity. The timeline for confirmation, however, will not be quick. Science rarely moves at headline speed. Even with Webb operating at full capacity, gathering enough data to rule out alternatives may take years. New telescopes, such as the proposed Habitable Worlds Observatory, could provide even clearer views, but those missions are decades away. This long timeline can feel frustrating to the public, especially when excitement builds quickly. But patience is not a flaw. It is a feature. Another layer of complexity comes from how scientific confidence is communicated. When scientists speak to each other, they use careful language filled with caveats. When that language reaches the public, it often gets simplified or exaggerated. Consistent with life becomes signs of life. Statistically unlikely to be abiotic becomes almost certainly alive. This is not malicious. It is a mismatch between how science communicates uncertainty and how humans prefer clear answers. Understanding this gap helps prevent disappointment. If future studies reduce confidence in the biological interpretation, it does not mean scientists were wrong or dishonest. It means knowledge evolved. That evolution is the real story. Beyond K2-18b, the search for life is expanding rapidly. Thousands of exoplanets have been discovered. Hundreds fall within habitable zones. Many more await detection. Statistical studies suggest that planets are common, water is common, and organic chemistry is widespread. Life, therefore, may not be rare. But detectable life is another matter. Even if microbial life is abundant, technological civilizations could be extremely rare or short-lived. Earth's own history supports this caution. Life appeared quickly but intelligent. Tool-using species appeared very late, and only once, as far as we know. This suggests that life is resilient, but intelligence is fragile. K2-18b, if inhabited, would likely host microbial life, not advanced civilizations. That is not a disappointment. It is a revelation. Microbes are powerful. They shape planets. Earth's atmosphere, oceans, and surface chemistry were transformed by microscopic organisms long before complex life appeared. Life does not need intelligence to be significant. It needs persistence. Another important implication of discovering life elsewhere is how it would affect future exploration strategies. Currently, many space missions focus on Mars, Europa, and Enceladus, places close enough to study directly. Exoplanets force scientists to rely on remote sensing. If life is confirmed through atmospheric analysis alone, it validates this approach and encourages investment in more powerful space telescopes. It would also influence target selection. Instead of focusing exclusively on Earth-like planets, scientists would broaden their criteria to include exotic worlds, sub-Neptunes, ocean worlds, and planets with thick atmospheres. Habitability would no longer mean Earth 2.0. It would mean chemistry that works. Finally, there is the human dimension. Discovering life elsewhere does not answer philosophical questions about meaning, purpose, or destiny, but it reframes them. It tells us that the universe is not indifferent to complexity. It allows life to emerge. That knowledge can inspire humility without despair. We would not become less special. We would become less alone. In the final part, we will bring all of this together. We will ask what comes next, how future generations may look back on this moment, and why, even if K2-18b turns out to be lifeless, the search itself changes how we understand the universe. If there is one thing the story of K2-18b and the James Webb Space Telescope teaches us, it is that science does not move forward in moments of absolute certainty. It moves forward by narrowing possibilities, ruling out explanations, and slowly improving our picture of reality. What makes this moment special is not that we have found life beyond Earth, but that we have reached a point where the question is no longer speculative in the abstract. It is now anchored to specific data, specific planets, and specific measurements. For the first time in human history, we are not asking whether life could exist elsewhere in the universe. We are asking whether it does, on a world we can name, locate, and observe repeatedly. That shift is profound. K2 and 18b may or may not host living organisms. The molecules detected in its atmosphere may eventually be explained by unfamiliar chemistry rather than biology. Future observations could weaken the case, strengthen it, or complicate it in ways no one currently expects. But regardless of the outcome, something fundamental has changed. The universe has become testable in a way it never was before. For most of history, the question of life beyond Earth belonged to philosophy, theology, and speculation. Even in early modern astronomy, planets were dots of light, and stars were unreachable. The idea of studying the chemistry of an alien world's atmosphere would have sounded like fantasy. Now, it is routine. The James Webb Space Telescope is not searching blindly. It is following predictions made by decades of physics, chemistry, and planetary science. It is testing hypotheses generated by models that can be refined, corrected, or discarded. This is what mature science looks like. One of the most important lessons to take away from this story is how careful language matters. A 99.7% chance of life is not a declaration. It is a statistical description of how well certain explanations fit the data compared to others. That distinction protects science from overconfidence and protects the public from misunderstanding. It also reminds us that uncertainty is not weakness. Uncertainty is information. When scientists say they are not sure, it does not mean they know nothing. It means they know enough to identify what they don't know, which is often more valuable. the search for life beyond Earth is, at its core, a search for context. Life on Earth evolved under specific conditions, but those conditions may not be unique. The chemistry of carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus is universal. Water behaves the same everywhere. Thermodynamics does not change its rules at interstellar distances. If life emerges where chemistry allows complexity to persist, then biology may be a natural outcome of physics, not a cosmic accident. That idea does not diminish humanity's significance. It reframes it. We are not less meaningful because life may exist elsewhere. We are more connected. Another important realization is that discovery does not require contact. Finding life does not mean meeting it, communicating with it, or even seeing it directly. Most life on Earth is invisible to the naked eye. Most of Earth's history was shaped by organisms that never built civilizations. If K2-18b hosts life, it is likely microbial. That does not make it trivial. Microbes transform planets. They change atmospheres. They regulate climates. They rewrite chemistry. Earth would not be Earth without them. Understanding alien microbes would teach us as much about life's possibilities as discovering advanced intelligence, perhaps more. Looking ahead, the future of this research is both exciting and restrained. New observations will refine atmospheric models. More exoplanets will be studied. Statistical patterns will emerge. Scientists will learn which biosignatures are reliable and which are misleading. False positives will be identified. New surprises will appear. Some planets that look promising today will disappoint. Others currently overlooked will turn out to be more interesting. This is normal. Science advances by being wrong in useful ways. The next generation of space telescopes will improve resolution, sensitivity, and wavelength coverage. Direct imaging of Earth-sized planets may become possible. Comparative planetology, studying many worlds instead of focusing on one, will mature, and with each step, the question will shift. Not, is there life out there, but how common is it? How long does it last? How does it change its planet? Those questions are deeper, harder, and more interesting. There is also a cultural dimension to this moment. For centuries, humanity placed itself at the center of existence. Then we learned Earth is not the center of the solar system. Then we learned the Sun is not special. Then we learned the Milky Way is one galaxy among billions. The possible discovery of life elsewhere continues that trajectory, not by diminishing us, but by placing us accurately within a vast system. Perspective is not loss, it is clarity. If life exists on K2-18b, it will not answer moral questions or solve human problems. But it will quietly tell us something powerful, that the universe produces complexity naturally, given time and the right conditions. And if life does not exist there, that knowledge is equally important. It tells us that biology is more fragile than expected, or that our detection methods need refinement. Either outcome moves understanding forward. That is the final, often overlooked point. Science is not a quest for comforting answers. It is a process for discovering what is actually true, even when that truth is incomplete, provisional, or counterintuitive. The James Webb Space Telescope did not find certainty. It found possibility. And possibility, when grounded in evidence, is where discovery begins. For the first time, humanity is not merely wondering whether life exists beyond Earth. We are building the tools to find out. That is not the end of the story. It is the beginning of a much larger one.